Okay, folks, today we're going to be talking about the substitution rule, or more specifically, U sub. And so this should make, hopefully, the rest of the AP Classroom FRQ make a little more sense. So I'm just going to go through the general idea, and then I will do a couple of different examples. All right, so we can use the substitution rule to find integrals or antiderivatives of functions that aren't either trivial or can't use one of the basic rules that we have used before, like the power rule for antiderivatives. So here's a function where that's the case. There's not really a way to simplify this. I mean, I could write it as 2x times 1 plus x squared to the 1/2 power dx. But there's not much I can do beyond that. I can't distribute the 2x because order of operations says I need to deal with the exponent first. And so there's nothing really to simplify here. So what we're going to utilize is this technique called U sub. And I just want to remind you about some notations here. First of all, the Leibniz notation that we use for a derivative, right? So let's say I have this function y and I want to take its derivative. I could show that by dy dx, and that means y prime, right? And the Leibniz notation is useful because it's like our delta y over delta x, which is something we learned in Algebra 1, right? But this means a finite change in y over a finite change in x. When I say finite, I mean between 2 points, right? Whereas the dy dx, remember, this is an infinitesimal small change in y over an infinitesimally small change, in x, okay? So with that in mind, as long as we understand that dy and dx are just infinitesimally small quantities, we're going to now be able to treat this dy dx like a fraction, okay? And the other thing to remember is that when we set up an integral, this dx, remember, comes from when we used rectangles to approximate the area under a curve. It was a delta x, and then we let the number of rectangles approach infinity, so delta x became infinitesimally thin, okay? So it has the same meaning. It's an infinitesimally small quantity as it does in our Leibniz notation for derivatives. All right, so now how do we do a U sub? So the best way, I think, to look at this is I'm just going to walk you through an example. And the idea, the overarching idea, is that we want to get our integral in terms of a new variable. And to do that, that's going to mean we have to focus on getting our differential. That's what this guy is called by itself. We want to get our differential, in terms of that variable, okay? Because that's what tells us what our variable is and what we're taking the antiderivative with respect to. So I'm going to write this integral on the next page. So it was the integral. What do we have? The integral of 2x times the quantity 1 plus x squared dx. All right, so we generally call it a U sub because a lot of times we use U as our replacement variable. So what I want to do is get things in terms of U by choosing a substitution to make. Oh, I just realized I forgot the 1/2 power there. Rule of thumb, it's not going to make sense really in the first one, but if you have nested functions, you try and choose u to be the innermost function. So I'm going to let u equal 1 plus x squared here. And the idea is that I want to get everything in here needs to be in terms of u by the n. I need to account for everything. So the first thing I'm then going to do is take the derivative of u with respect to x, because u is now a function of x, right? And so if I take the derivative of that function u in terms of the variable x, well, the derivative of 1 is 0, the derivative of x squared is 2x, okay? Now we're going to treat this like a fraction, and I'm just going to multiply dx by both sides. So now I'll have things in terms of du, and I'll notice that du equals 2x dx. Well, this is actually going to work out perfectly for me, because like I said, I want everything to be in terms of u. So let's note what I did. This 1 plus x squared, that's all getting replaced with u, because that's what we let u equal, right? And notice that now du equals 2x dx. Well, note that what I have left over is 2x dx. So now we can rewrite my integral completely in terms of u. So my integral is going to become the integral of u to the 1/2 power. Notice that 1/2 was still up there. And that 2x dx gets replaced with du. And now it's just like we're looking at a whole new integral problem, right? And so we can kind of, for now, ignore everything else and just focus on finding the antiderivative of u to the 1/2. Well, that's one that we can use the power rule for, right? So the power rule for antiderivatives, let's see. Remember, it's if we have the integral of x to the n dx, that's x to the n plus 1 over n plus 1. So in our case, we're going to come out with, let's see, add 1 to 1/2. So I'm going to have u to the 3/2 divided by 3/2, which is 2/3 u to the 3/2. And then, of course, I want my answer back in terms of my original variable. So what I want to do is then just go back and replace u with 1 plus x squared. And so what we end up with is 2/3 times the quantity, 1 plus x squared to the 3/2. And then don't forget, for any general antiderivative, we're going to do a plus c. So when it's not a definite integral, when I have an indefinite integral, I need to remember to put that plus a constant at the end, and there's my final answer. All right, so we can always check that answer, which is right here, by differentiating it and making sure we get back to the original integrand. So if I take the derivative of this with respect to x, first of all, we know that the derivative of a constant is 0. And here we're going to have to use the chain rule. So derivative over the outside, we would bring down the exponent, multiply the exponent by the new coefficient out front, and then multiply by the derivative of the inner function, which would be 2x. Simplifying, you can see, yep, we get right back to that original integrand that we had. So here's kind of a version of the substitution rule. I don't know how useful it is. You don't need to memorize it. It's really going to be a procedure where there's going to be a little bit of guess and check the first few times, but I can kind of prove it to you. So what it's saying is, if we have an integral in this form, and if we let u equal g of x, then notice that du dx is g prime of x, and that means that du is g prime of x dx. So now I can replace the g prime of x dx here with du, and I can replace g of x with u, and that gets me over here to the integral of f of u du. All right, let's try a couple more examples. So again, rule of thumb, we just kind of guess and check, or we'll try and use the innermost functions if there's a series of nested functions. That's not always the case. And then you're just going to try something. All right, so in this case, I do see nested functions. I do have an inside function, which seems to be x to the fourth plus 2. So I'm going to let u equal x to the fourth plus 2. All right, so then du dx is 4x cubed. Okay, so du is 4x cubed dx. All right, so let's check on some things. I know that I'm replacing this with u, right? And then the other thing I have to account for is the differential. I need to get my dx. I need to be able to replace it with du somehow. So, okay, I have that du equals 4x cubed dx. Well, I don't have 4x cubed dx, but what I do have is x cubed dx. So when all that your differential differs by is some constant multiple, we can deal with that. We can just divide it out, right? And I can say that, oh, okay, so 1/4 du is x cubed dx. So now when I write my new integral, it's just going to be the integral of cosine of u. And then remember what we replaced the x cubed dx with is a fourth du. So I can say times a fourth du. Properties of integrals say that if I have a constant multiple, I can pull that out of the integral. So 1/4 integral cosine u du. Now everything's in terms of u. Antiderivative of cosine is just what? Sine. So I have 1/4 sine of u plus a constant because this is indefinite. So that's 1/4 sine, putting it back in terms of my original variable. U was x to the fourth plus 2. So x to the fourth plus 2 plus c. And again, if you want to check your answer, differentiate this, and you'll note that you get right back to the original integrand, which is x cubed cosine x to the fourth plus 2. All right, so how do we deal with definite integrals? Definite integrals are kind of nice with u sub because it's going to allow you to skip that last step of having to go back to terms of your original variable, as long as you update your limits of integration. Remember, a definite integral is really a fancy way of writing a number. It's a number that represents the net area of a curve over the interval. But it's still just a constant. So what we're doing when we u sub is writing it in an equivalent form with new limits of integration. And so the idea is if we let u equal g of x, well, my original limits of integration were specific to being in terms of x. So now that I've updated all my variables to be terms of u, I do the same with my limits of integration. So I go, oh, okay, well, what would u be when x is a? Well, u would be g of a, because I would just replace x with a. And that becomes my new lower limit of integration. Well, what would u be when x is b? Well, replace x with b, u would be g of b, and that's my new upper limit of integration. And then I can just evaluate that definite integral in terms of u. I don't have to go back to terms of x, because what I have is an equivalent number, an equivalent net area. Okay, so it'll give you the same exact value as it would if you left it in terms of x. All right, so let's show you what I'm talking about here. Integral from 0 to 4 of the square root of 2x plus 1. So right off the bat, I'm just going to try something. Let u equal 2x plus 1. All right, then the derivative of u with respect to x is just going to be 2. So du is 2 dx. I don't have 2 dx, I just have dx, but that's okay. Whoops. When it just differs by a constant multiple, we can deal with that by dividing out the constant multiple. And I get, oh, okay, so 1/2 du is dx. And my new integral becomes the integral, and I'm going to hold off on the limits for a second, the integral of the square root of u, and then dx gets replaced with 1/2 du, so I'm going to put the du there, I'm going to put the 1/2 in front. All right, so now to update our limits of integration. So remember, we want to think when x is my lower limit, which is 0, u is going to be 2 times that 0 plus 1, because that's the way I defined u, right? 2x plus 1. So u is, oops, oh no, undo. Well, I just accidentally hit the erase all key, so give me 1 second to restart this. Oh boy, u equals 2x plus 1. Du dx is 2, so from that we got the 1/2 du equals dx, and my integral became integral root u du, 1/2 out front, and we just found out that my new lower limit is going to be 1. Cool, so for the upper limit we'll say when x is 4, u is 2 times 4 plus 1, which is 9. So my upper limit is 9. All right, so what I have is an equivalent definite integral. So I'm just going to use the fundamental theorem of calculus part 2 to evaluate this. I'm going to write it in a form that's a little bit easier to do calculus with. So u to the 1/2 du. If I add 1 to the exponent, that's 3/2. So I'm going to have u to the 3/2, and I'm going to divide by the new coefficient, which is going to give me 2/3 u to the 3/2. Okay, I'm going to evaluate that from 1 to 9. So this is going to give me 2/3 times 9 to the 3/2 minus 2/3 times 1 to the 3/2. Oh boy, let's see. What's 9 to the 3/2? I'm not gonna lie to you guys. This is going in the calculator. And you guys are gonna have full access to your calculators for the AP exam. So don't bother doing stuff like this in your head. So this comes out to 18 minus 2/3. All right, so that's going to be 54 minus 2 over 3, which is 52 over 3. All right, there's our first definite integral example. The other thing you can do is remember about symmetry. If you know the symmetry of a function, so if a function is even, sometimes it makes it easier. If I'm trying to integrate from negative a to a, I can instead just integrate from 0 to a and multiply by 2. And that just makes calculations easier, because when one of your limits of integration is 0, it's just a lot quicker to plug in. But again, you guys have access to it. The other thing is, if it's an odd function, if it's symmetric over an interval and it's odd, it's going to be 0, because the negative area, the area below the x-axis, just cancels out the area above the x-axis. And so like an example where something like that might be helpful is here. This is an even function. And remember, the condition for even function is that f of negative x equals f of x. So instead of integrating from -2 to 2, we could do 2 times the integral from 0 to 2. I'm not going to go all the way through that one. These are just some tricks to make things faster. Now, this one, it is good to know this trick, because if I ask you for this integral, this is a huge messy function. There's not really a use of that you can do for this, but if you can recognize, okay, if I plug in -x, these things aren't going to change, because squaring a negative and raising a negative to the 4th power makes them positive again, right? But tangent is odd, meaning if I plug in -x, it's going to change its sign, and then that negative can just come all the way out to the front, and I'm going to get the opposite of what I would have had if I used +x. So the fact that knowing this is odd over this interval from -1 to 1 saves me any work, and I can just immediately go, okay, that's 0. The other thing with definite integrals is that your calculator can compute definite integrals for you immediately, so I'll post a video of how to do that fairly soon. All right, good luck with this section, guys. Hope to see some of you at office hours.